Hello, welcome to our session on functions and calculus. And I see we have arrived at about the middle of module 1. Nice to see you all here, at least virtually online. And what we're going to do now, entering the section entitled Functions and Calculus, we're going to look at the relationship between a mathematical function and a computational model of a biological process. Right, let me try to share my screen. I think before we go into the session itself, I'll show you that on our Moodle page, under where it says web tutorials in the section 5, so session 5 for today, or assignment 5, functions and calculus 1, there are some older video clips of a similar content as we're going to do today, but particularly I have just uploaded the code that I'm going to use today, which is the MATLAB code here, and also the slides that I'm going to show with the equations and explanations. So if you just want to click for them, I think you can then either copy and paste or download the PDF here. And code is, of course, is a MATLAB code here that we are going to run through. Right, so let's come back to the overview. So I will record this session and will give you a link later on so that if you want to see that again, you can also do so. So our structure is simple. We start with looking at a linear growth function to get into the terminology, and then we'll do simulation of an exponential growth model. Right, so not at a function, but at a model, and then we look how that relates to a mathematical function similar to the one of the beginning. And we do that in 2 iterations. And if we have a little bit time at the end, we can do some more algorithmic thinking, but we all, I think, want to make sure that we'll stop by 12 o'clock today. Right. Let me just stop showing the video so we have more space for our actual content. So this slide here on the, just a second. Yeah, so this slide here shows a mathematical function, and it's the description of a process of linear growth. So if you have studied the materials, you know what that refers to, some cylinder that grows at some rate or something. So the important thing from a mathematical point of view that we have an equation of the type V equal and then something on the right hand side. So V is in some volume here, and the function that we have, which is on the right hand side here, initial volume plus growth rate times t, tells you and gives you a way of elaborating how that volume of some rod or whatever you look at, how that evolves over time. So it's a dynamical system, it changes over time. And specifically, we have this case of linear growth here, where the volume will just go larger the more time advances. And then in addition to sort of having a check what time it is, we also need to have 2 parameters or numbers. One is the initial volume, where at the time sort of 0, the starting point of your experiment observation, what is the initial volume that you start with, from which you get off, and then what is the growth rate. So that is sort of a constant that tells you or that gives you a quantification of how much per time step the volume will increase. and taken those two components together, you add them together, you calculate the volume. And this is referred to as a continuous time model. It's not a model, it's a continuous time function. So continuous time function, because continuous means you can calculate the volume for any time that you wish. So you don't need to go in order. You can calculate it for what is the volume after 5 seconds, or after 25 years, or after 7.635 days, right? So for any point, any real number that you can come up with, you can calculate what the volume will be. So this is nice, but it's of course requires that you know this function in detail. And of course you can do that, you can calculate it, you can fit those parameters. There's examples down here. If you know where to get those numbers, say from experimental measurements, you can maybe prepare an initial volume, and then you can see in some experiment how much does it advance per unit of time. So you have the growth rate per unit of time. You can then get an idea of that function. You can write down the function, and then it's all done. So this is not a model, but in the terminology of modeling, what we are doing here, mathematical modeling using MATLAB, this is the solution of a model. So let's go to a slightly more complex example, and that is the example of exponential growth. And here we'll have both. We'll have a model and we'll have the mathematical formulation later on. So what we'll do, we'll start by looking at the model that produces that growth, right? Previously we had linear growth, so you can imagine how would you create such a growth? Well, you can create linear growth if you just add a certain amount of volume every unit of time. Right? So you start at some time point, then you wait a certain amount of time, and then you add something to it, because the volume will have increased. And similar, we can do a growth model for, in this case, say, the population growth in a continuously fed cell culture. So you have a continuous volume, well stirred, and you have some cells initially there, and those will divide, so the population will grow. And the growth model that you can extract from observing real, say in a chemostat, how that actually evolves over time, you will get an exponential growth model, namely that there's a certain, at least in the initial phase, that there's the observation that a population within a certain amount of time doubles. So doubling is not just adding something to it, but multiplying it by number 2, right? So from this you can infer a model, and the model is written down here in that yellow box, that the population at time nj, so at a time point j, you can calculate it from a previous time point, nj minus 1, by multiplying that previous population with a factor of 2, which is just doubling. And now you say, what is this j, right? What time is this j? Well, j can be any number, any integer number, just in steps. These are just steps that you take, and you have to define what does a step mean. So in this case, because we have said the population doubled, of course, from one step to another, this is just the doubling time. So this is flexible. This can be short or long. So if you have microbial cultures, that may depend on whether you have this bacterium, E. coli, or whether you have that yeast, or you have Aspergillus niger to synthesize citric acid, for example. So that's what we have here. We have a discrete time population model, discrete time in terms of doubling time now here. Now this is of course something that's a bit particular in the sense of you don't really want to set up models in terms of the doubling time, which is something which is very specific for a species, like it doesn't apply for other species that have other doubling times. So what we can do is we can refine this model a little bit and write down the same model, growth model of that population in terms of unit time, just per time unit, what happens here. And here's the version. It's very similar to what we had before. And the only thing that changes is that instead of a factor 2, which is the doubling, which means it's then expressed in terms of the doubling time. We just say we have that in unit time, so per time unit, what happens. And then if you have seen the materials for this course, what we need to know is the fractional growth. So by what fraction does this population grow in a time unit? And if you know that fractional growth, which is R, which you can actually calculate directly from knowing the doubling time, then you put 1 plus R in front of this and multiply the population number to get the future population from the current population, or you get the current population from the historically previous population in steps of time units. So the calculation is some function that we just need to know. It's called fractional growth. R is the fractional growth, and we multiply with 1 plus R. Why? Because if R is 0, means the fractional growth is 0, right? What does it mean? The population doesn't grow, it just stays the same. And then we have the new population is the old population times 1. It just remains what it is. So that's why we need to have 1 plus R. And then if R is some percentage, like 10% or 15%, then every time unit you will have a growth of 10 or 15% if you add that to 1. Right, so let's take what we have found out so far about the discrete time model, implement that in MATLAB, and then we'll have a look how that relates to an actual mathematical function similar to the one that we saw at the beginning. So now we need to start coding, right? So I have now prepared for you a template which I have opened here. And that template will hopefully help you with those headers that I have put in here, help you find a little bit of orientation of where we are in that process of elaborating the code. So functional calculus on, we know that already. The discrete time model, I have just repeated it here such that we remember what it looked like. So if we start with that very primitive thing in terms of doubling time, we know that nj is calculated as 2 times n times 2 times nj minus 1. So how do we implement that? And you can see the instructions that we have. So we first clear everything, and then first we need to define all the things that we need to do the calculation. So if we do in terms of doubling time, of course, we need to define the doubling time. So there's this famous number, it's very artificial, but it's supposed to be 20 minutes for E. coli doubling under certain conditions. So if we just assume the doubling time is 20, say minutes, but that's only in parentheses. MATLAB is of course agnostic to time units, but if we define 20 as representing minutes, then it's the doubling time of 20 minutes. And then we want to look at this process of exponential growth, what it will be, the growth of the population over time in terms of some repeats. So let's say 6 repeats of that period of 20 minutes to come to a 6 times 20, 120 minutes, which is the simulation of a time period of 2 hours. So then we need to, of course, define our time points. Time TPS, I define a variable which is now going to be an array or a vector that starts from time equals 0. So how many time points? The first time point will be 0, and we go all the way up to how many time? 2 hours. If we want to simulate 2 hours, that would be the doubling time times the repeats. So we go from 0 to doubling time times repeats from 0 to 120, that is. And we want to go in steps of what? In steps of doubling time, right? That's what we said. We make our model in terms of the doubling time. So we need to put that in. It's 20 or d time, which is more precisely for from a computational perspective, we use parameters instead of the actual numbers. So now we have that set up from 0 to doubling times repeats in steps of doubling time. So that will be 0, 20, 40, and so on up to 120. So if we have this, now the number of time steps, now we need to know how many times do we need to calculate. So of course we can guess if we have 6 repeats, it will be 7 time points. If we start from 0 and end up at 120, and we have 6 repeats in between. So let's nevertheless do a nice computational implementation of this. We can get this from the length of the TPTS. Why is that? So I put a semicolon to suppress it because, of course, TPTS is the time points that we need to calculate, and the length of that vector will just tell us how many there are. Okay, and then we need to have our results vector. Our results vector is the population vector. So if I represent a population with capital N, then our population, we can initially have everything set to 0 as we have learned. So we set up a 0 population vector by using function zeros. We have a single population. So if we had a model with multiple, we could do multiple, but here we have a single. So we start with 1. And how many time points do we have? Well, NT, we just calculated, right? The number of time steps is NT, so number of time points we put there as the length of the population vector that we want to calculate. Right, it's not quite finished because, as you know, we need to somehow start with a number. So our first point at time point 0, because it's all zeros, that will also be zeros. So if we want to start with a population that is not exactly 0, and then we would have to define what is the population at time 0, which is the first entry to this vector. And let's just give it an arbitrary number. I think in the materials it's 100. So this is, of course, crucial because if we start with a population of 0, then doubling the population is 2 times 0 will not lead us anywhere. So if we have 100, then after the doubling time, we should have 200, and then we'll start to grow and so on. So let's do a simulation of that model that you probably still remember. And we do that in the same way that we have now got used to. We use a for loop and some index j that runs from 2 to the end. And what is the end point is nt, is of course the number of time points. So we want to have starting from 2 because 1 is given, right? Population at time point 1 is given already. So from the second population onward, all the way down to nt, we want to have that calculated, the population number, and we're going to say that the population at time point j, so 2, 3, 4, and so on, can be calculated from the population at time point j minus 1 by multiplying it with 2 times 2. You can put the 2 in front or afterwards, doesn't really matter, but by doubling the previous population. So that's 1 doubling time passed, 2 times the old population number is what you get. And then because it's MATLAB, you need to put an end at the end. And you can see syntactically, because 4 and end are in blue, that looks to be correct. And if that successfully works for all time points, then we should have that population vector filled up, and we can go and plot it. And we plot the time points that we defined originally. What was it? TPTS time points. And of course, we plot that population vector n. And if you remember, that MATLAB by default makes lines between, if we just want to know the population at those discrete time points that we have calculated, rather than have them connected with lines. What you can do is, in single quotes, you can put a symbol like a star or something. And K, that will be the star, will be the symbol or the marker for the time points, and K will represent the number, the color black. And I think there's a parenthesis missing. It's now closed, and we can check the code and see if it works. So it seems to work. It gives us a couple of time points, and we start from 0. That's our 100 population that we have initialized, and at doubling time 20, we have doubled to 200 and so on. And we can see it starts to grow, and it grows faster and faster. Every step that we take, the growth will be more, because of course doubling is applied to itself. It's not just adding every time 100 population cells, so to speak, but it's doubling whatever is there. And that is the beginning of what we then will be. You can do a longer simulations. What will be an exponential growth curve? Exponential growth curve, of course, being at the heart of many, many different processes, including pandemics, as we have it currently witnessing with viral growth rather than bacterial growth in a cell culture. Right. So that was our model, and we have it simulated. And now we want to go and refine that a little bit. We want to do the whole thing in steps of 1. So if you allow me, I'll go forward. We have a new formula that we remember from the beginning. It's now the number 2 is replaced by 1 plus r, that fractional growth rate. And so what we can do is we can use a couple of things that we did before. Just copy what we had before in terms of doubling time and repeats, because we want to simulate the same thing that we did before. But what we are going to do now is we're now taking steps of 1. So we want to have now the model expressed in terms of unit time. So for every time unit, we want to have the time point, the population calculated. And so that means we can also use the initialization of the population vector. I just copy this. Because that will be the same as before. We will also have the number of time points as before. So, and nothing has changed really so far. But the one thing that is new is that we now need to calculate the fractional growth, or that rate constant r plus 1, in terms of the doubling time. So nothing has really changed so far, except that we are now going in steps of 1. So where's that expressed? I haven't really expressed it, so we need to do that. So we need to have the time points. Where's our steps of 1? And instead of doubling time, we now go in steps of steps. Right? So start from 0, go to the doubling time times repeat. So go for the 2 hours that we had before, 6 times 20. But now we go in steps of 1. Actually, in MATLAB, you don't really need to define that. What you could do, you could actually take that away, because MATLAB by default will give you an array in steps of 1. But let's do it explicitly here so that we know what we are doing just while looking at the code immediately. Right, so that's now setting up our time array, and now we need to calculate the fractional growth and add 1 to it. So I just call it r plus 1, just, it's just the name, right? It's just a string, but to remember what it is. So r plus 1, and according to this formula here, which you find in the session PDF, what is it, equation 1.1.4, something in the material for this session, of course, is calculated as 2 to the power of, and then you do 1 divided by and the doubling time. So do we have that defined? Doubling time is 20, so 2 to the power of 1 over 20 would be the fractional growth r plus 1 as we need it in our model. And if I go up again, and I just copy that code from that we had before to simulate and plot the model, take that down and simulate and plot that model. So the change that we have now, we don't have a multiplication by 2, but we need to replace that with r plus 1. So this is what we have just calculated up here, semicolon. So we have calculated that now with every time step, we have a fractional growth of that population times r plus 1. And we have a simulation that goes from 2 to nt as before, just every time steps calculated to fill that population vector. And of course, we can now use the code as before and make our simulations. So something went wrong here in line 52. So let's debug the code. Unrecognized function or variable nt. So I have done here, I have removed all the previously defined variables. So I need to define nt. If I just go up, which is the number of time steps. And I just put that somewhere here. Where is the number of time steps? So we needed to set up our population vector. So before we set up the population vector, we have to define what it is, right? So you can see the logic. You first calculate the time points. Knowing the time points, you get the number of time steps. And then you can set up your population vector in order to have your simulation correct. So after debugging, we can see that exponential growth now in steps of unit time. So for every minute, so to speak, model minute, we have now the exponential growth simulated. You can still see it's discrete. So if you go closer and closer, so that's still discrete points, right? But, oops, let me just go back to the original, where is it? Yeah, something like this, 0 to 120. This is now simulated in a very generic fashion, right? So it's a generic way of simulating per time unit. You have a simulation, and you can predict now, knowing that the initial population was 100, so 100 cells at incubation. You have incubated your culture with a few cells, and then you can sort of simulate if that model applies, namely if there's a certain fractional growth per time unit, and this is continuous over all time, so there's no changes in nutritional or ambient temperature or so on, then we will have predicted the outcome of the model, namely that exponential growth of that cell culture, in that case, model, giving us an estimate, and of course also allowing us to adjust the model if we find that it disagrees with the experimental measurements. Then we might, for example, say, well, the curve looks similar, but it goes faster or slower, and probably means that the fractional growth is not estimated correctly in the model. Right. So if I just keep this figure here in the background, and what we want to do now is we want to see how this simulation, sort of discrete time simulation, which is representative of what normally we do in computational modeling, namely discrete time simulations and then plotting them in a way like this, how that relates to a mathematical function of, in this case, exponential growth. So when you remember that rod volume, or whatever volume that was in the beginning, that linear growth, that was a very simple mathematical function, linear function, but now it's a more complicated function that simulates the process that we are seeing here in this graph, and that's called the exponential function. So what we can do, can now go to the continuous function, and that's called the exponential function. So the continuous exponential function, and if you like, that is the solution of that model, right? The solution, if we set up the model like this, as we did it with our discrete time mechanism of having a fractional growth, then we can say there is a corresponding mathematical function that actually allows you to predict the shape of the curve and calculate all future populations without even doing a simulation. So for that exponential function in MATLAB, this is called something like exponential function, and you apply that exponential function to time. So if you have time going on continuously, then the exponent e to the time exponent of the function, this is the way to express the exponential function. And in this case, what we will have to have, we have a certain time constant to arrange whether this function grows quickly or slowly. We can use a rate constant, a growth rate constant, k, which, however, is something that we need to calculate. And this is what we are now trying to do. So how can we set up this exponential function with that k as it is defined here? So first we need to calculate the k, right? So what is the k? It just says the formula here, equation 1.1.5 in the PDF. It's the logarithm of the quantity that we had already defined previously, which was 1 plus r. So we can take that, right? If it's still there, check in our workspace, is it still there? It's called r plus 1, it's still there, so we can do that. And we calculate it by taking the logarithm of r plus 1. Close the parentheses, semicolon. And that is now the way we define. Actually, the natural logarithm in MATLAB, if I remember correctly, is log rather than ln. Mathematically, we say ln for natural logarithm. In MATLAB, that's log. So the function log to calculate from r plus 1 that rate constant k, which we need to adjust that mathematical function, knowing the fractional growth r and having that expression r plus 1. And what will be our initial population? So we need to have an initial population y. So let's assume for a second that we're looking at the value of the exponential function at t equals 0. So here's our exponential function. And if t is equal to 0, then of course k times t, whatever k is equal to 0, every function taken, and every expression taken to the power of 0 is equal to 1. Right? So whatever you do with that k, this value will be 1. So it means we will always, exponent to the power of 0 is always 1. So 1 means that is our initial population. At time 0, we'll have an initial population of 1. But if we want to adjust that to something else, we just need to adjust it by multiplying with something else. So what we can do is we can define our initial population. So sometimes we do n sub 0. So the n at time 0. But of course, it will if we want to compare the continuous function with the simulated model, that would be the same as we had before, namely the first value of that population array n. So in this case, it will be 100 because we set that equal to 100. And we need that to adjust the exponential function to start with the same initial population. So let's define this function, and as we have done it before, we use our function called fun as an implicit function, an anonymous function. So we use the @ symbol to define the variable. The variable will be time, of course. How does it grow with time? And our function is now the exponential function applied to k times t, as we have done it before, but adjusted for this initial population means it will be multiplied with n0. So remember, if the time is 0, then the expression exponent to the power of 0 is 1. And then if we have it multiplied with 100, 1 times 100 will have an initial population of 100 as before. Right, so that's our anonymous function. And for plotting this whole thing, we want to have the limit specified. So we want to simulate it as we did before, namely starting from 0 and going to nt, the number of time points, whatever that was. Just let me check if that's still defined. Nt is still defined, 121 values going from 0 to 120 plus the 0 value, that's 121 numbers. So let's go do the limits from 0 to nt. And then we have it set up, so to speak, and we want to, what does it say here? Keep the previous figure. So keep the previous figure means we need to give a command, which is hold on, which says if we have that figure in the background, don't erase that, keep that here. So I want to keep that. I want to have our new plot on top of it. So we do our new plot. And that will be fplot because we have an anonymous function. We plot our function in the limits, and we can, what can we do? Give it a certain color, say magenta or red, whatever you like. So M for magenta. Let's check the whole code that we have done. So we have defined our growth constant k here. From the r+1 value that we had previously, we have defined that the population initially should be the same for this mathematical function as we had in the simulation. We have defined our function using that initial population and the growth constant k. And then we say within the same limits as before, we want to have that function plotted. So I execute the code. And it's actually already there, but it's not so easy to see. So I make a small adjustment and I say line width, what was it, line width, I think, and make it a little bit thicker. So run that code again. And now we can see better. In magenta is now the exponential function. Of course, this is a very nice result because now we have the simulation, the computational model simulated. These are the star markers that we can not really see, but we can zoom in and see if we can make that a little bit bigger. The individual markers, that was the simulation, the discrete time simulation. And in magenta here, with that line, we have the continuous, the mathematically continuously defined function, which is the solution of the model. So the solution meaning, never mind the individual time points. For every time point, you can calculate it, and you can see those things fit very smoothly over the whole range from 0 to 120, still a little bit more. And that's our main outcome. So now maybe a couple of comments. So first of all, we have an agreement that is perfect. In this simple case of simple model of exponential growth in cell culture, this is perfect because the simulation can directly be converted to the exact mathematical function that lies behind it. So there's a mathematical solution to that model, so to speak. So the bad news is, for any reasonable biological model, for just about anything that you want to simulate computationally, there isn't an exact mathematical solution. So that's why everything that we do today, whether it's the weather forecast or the predictions of pandemic, number of cases or number of people who will die tomorrow in the UK, everything is predicted based on computational modeling, on discrete time models that, however, are complicated, too complicated to be solved mathematically. So there isn't a mathematical solution. It's just not there. So that's why we need to learn the art of computational modeling as well, not just a little bit about simple functions, because simple functions only get us so far. And on the other hand, then looking at this curve, where does it lead to if you just keep simulating? So not for 2 hours, but for 20 hours, 200 hours, what will happen? Well, that function as well as the model will grow to eventually infinity, right? If you just wait long enough, if you wait an infinite amount of time, both the function and the model will go to infinity. So we might not live long enough to wait or to reach that, but that's of course something that maybe is very unrealistic. So in a real-time setting, we expect neither the function nor the model to go to infinity. And why is that? What's the solution to this made-up riddle now? Well, the solution is that the model is, of course, not a good model of a natural process, right? It's nice to model that the bacteria population will double per unit of time, or that the COVID-19 cases will double from today until middle of April, but it's not a good prediction in a natural, realistic environment, because it's not just about doubling. There's other factors coming into play, and maybe other populations that also interact. And then there's processes in the pandemic case like vaccination, which are not yet implemented in the model. And in bacterial growth, it might be there's not enough nutrients for the bacterial population to grow, and so on. So this is then left for further sessions. To refine the model is then a different case, but of course limitations of the model, depend on what you put into it. So if we've put only one process into it, that doubling, so of course that only gets us so far. Right, so that was about the mathematical and about the practical consequences of that model. Okay, now let's just keep that in the background. Let's do a very small exercise to finish this up a little bit, something in a totally different spirit. Now to work with those things that we have here, those variables that we have defined in MATLAB, to ask a certain question. And one of the questions, I took that from the materials, is at what time is that population equal to 1,000? So you set a certain threshold. You ask a question, so to speak, and you want to answer that question by means of that model that we have developed and simulated. So the question would be, at what time does this population reach 1,000 according to the model? And first of all, we can just try to estimate that visually from the plot. So plot line at population equal 1,000. How do we do that? Well, in MATLAB, a line, we can use the function line in order to plot a line. And the convention to plot a line is square brackets, comma, square brackets. So the first pair of square brackets needs to contain the horizontal values, so from where to where on the horizontal axis, which however we know because we want to start at time point 0 and go to whatever the number of time points were, in this case 121, I believe. So we would go from 0 to 2 hours, and we want to have a line that stretches from 0 to 2 hours. And what we want to have now, we want to see a line, a horizontal line, at the value of the population being 1,000. So 1,000 is vertically, of course, a population that goes vertically. So the y value will be 1,000, and it will be so if it's exactly vertically, will be from a horizontal line. So it will be from beginning to the end. So it means it will start from 1,000 and it will end at 1,000. So let's see what that code does. If we execute the code, here's our line. So you can see at the value of 1,000 in that population, we have now drawn a horizontal line with this very simple code, the line function. And you can guess if you want to know at what time is that the case. So say, oh, it will be a little bit more than an hour, and you will have a population that is 1,000. If you started at 100, the initial value was 100, so it's 10 times the initial population, so to speak. Right, so that's an easy guess, right? 60, 70, 60 something, don't know what the exact value is. You can do it, of course, precisely, but just to say, visually, you can immediately estimate that number just by drawing this line into that graph. And mathematically, of course, we can do something slightly better, namely, we can check using find. So conditional statement, logical statement, conditional statement, where we want to know where is that population n, right? It's all numbers contained in that population vector. Where is it larger than 1,000? So let's do that. Let's not mind what happens with the plot. Let's see in the command window without semicolon. We can see the result in the command window. The answer is columns, and then it says 68, 69, 70, 71, and that goes till 121, so for the time points. So it tells you in that array n, just go back with this, all the positions from index 68 all the way down to the rest are numbers that are larger than 1,000, right? So you can see, very easy to find. And what we can do is we can assign that to a variable called larger 1,000, larger 1,000. And now we have that, if I suppress it now we have that number, that array from 68, 69, and so on, everything stored in an array called larger 1,000. But of course, we are not interested in 69, 70, 71, everything else. The only thing we are interested in is the first value. What is the first time point where we find a population that is larger than 1,000? Well, that's very easy to do because, of course, if I just clear that, it is larger 1,000. This is the whole array, and we go back and we say, what is the first value? And the first value is 68. So knowing that find gives you the position or the index of that number, now we know, at position 68 means time point 68, because we have simulated everything in units of time points. At time point 68, so after 68 minutes, we have reached a population that is larger than 1. And if you want to see the number, the population, the time where the population is still below 1,000, you can also do that. Just take 1 away. It's 67, it's below 1,000, 68 is above 1,000. So with that resolution that we have, we can find the time point easily where that population exceeds 1,000 or whatever value you choose. In this case, 1,000 is of course arbitrary. Right, so I think that was also a part of the assignment. So that concludes our short webinar on this, a couple of exercises that we did. If you look at the if you look at the slides, there's also then the extension. You can do the same thing with population decay. So exponential decay from starting from a large value, how will a population decay exponentially and reach a final value? And then the so-called logistic growth is a combination of growth and decay that will help you to model more realistically processes that neither go to infinity for growth or go to zero for decay, but reach some intermediate stationary population level, which is often desirable when doing biological modeling. So, but I leave that for you to check it. The MATLAB coding is the same, and all the principles of the relationship between the functions that you can get analytically and the discrete time model implementation is just as we did it today. Right. Thanks very much for joining me. A link to the video will be sent to everybody in sometime after the session when it's stored. And if you like, we'll continue with functions and calculus 2 and another webinar in 2 weeks' time. Same Zoom location, if you like. Bye.
Thanks very much.